Welcome, and thank you for joining us for the fifth and final seminar in our 2023 Science in the News Spring Seminar Series. Tonight's talk will have 3 parts, and in between each part we'll pause for questions, which we can take from the audience, or also if you're joining us on our YouTube live stream, please feel free to drop any questions that you have at any point during the talk into the chat, and we will relay those to our speaker. So, our speaker tonight is Kenneth Wang, a PhD student here at Harvard, and tonight he'll be telling us about, is your password in danger? Demystifying what quantum computers can and cannot do.
Okay, hello everyone. Thank you for coming. My name is Kenneth and I'm a graduate student in physics. And today I would like to tell you about whether you should be worried about your password being in danger or not. And we're going to demystify what quantum computers can and cannot do. So there's a lot of hype surrounding quantum. I don't know if people have been hearing about it. And I found this, I guess it's a magazine article that basically summarizes the talk, like, has the age of quantum computing arrived or maybe not arrived? And we will break down basically what that means and what you need to know to be able to make sense of that statement. And there's also, in addition to hype, just in the general news, there's also hype, with the government. So there's this great National Quantum Initiative, one of the few things that we can do in a bipartisan way. And there's been a $2.6 billion investment by the US government exploring the overlap of quantum and the government. So what is all this hype about? I think as we enter the new century, it's good to, this is one of these things that is emerging, and it'll be good for us to find out what it's really about. So, as the introduction said, we have 3 parts tonight. So I will give you a brief introduction to quantum mechanics, then discuss how you might use quantum mechanics to compute, and then also sort of a survey of the current efforts in both labs and industry to build these things. Sort of the crux is that these things are already coming online, if you did not know that. Okay, so let's get into an introduction to quantum mechanics. So in classical physics, and what I mean by classical is basically before quantum. It's kind of, in the sense that classical physics was not classical to the people who made it, but there's this distinction between particles and waves. And when we think of particles, particles are objects that can move around, can collide, and can hit each other, things like this. And waves are something that's more extended. So you can kind of think of like throwing a stone in water and then, you see these ripples coming out. And this distinction, back in the 19th century was thought to be pretty rigid. Like there are particles and there are waves. And these particles, one way to think about them is they have definite positions and velocities. So they are somewhere at some time and they are going somewhere. And they have an energy which is determined by the velocity. So if it's moving faster, it has more energy. Waves are kind of a different beast, so they're spread out across space and they change in time. There's some sort of way in which they change in time. And we'll go more into waves now, since I think, I was having this discussion before with somebody on how you actually really define a particle. It's actually not very clear, but waves are certainly something that we can more well formulate, and is a little bit more out of the daily realm. So waves kind of look like this. So you can think of this as sort of the height of the water as it goes up and down as a function of position in the case of the water wave. And when you take a snapshot of a water wave, you can define sort of an amplitude, which is sort of how high the water is going and how low it goes. And also a wavelength, so how far it is from one peak to another peak of the wave. And that snapshot will determine what we call the wavelength and the amplitude. So waves are characterized by sort of a wavelength and then also how big it is. And then when you sort of let time go and let time advance, waves can move. So here's an example of a wave that is moving, and once it's moving, it has a frequency. So if you look at one point, it will be oscillating up or down. So it's like if you watch into the water and you look at a point, then it's that point is going up and down. And it also has a velocity as a function of time. The water will spread out when you throw a rock inside of water. And then something else that's actually very interesting about waves, and this is sort of what gives quantum mechanics a lot of its weirdness, as we'll discuss, is that waves can interfere. What that means is that if I have 2 waves, let's say this one up here and then this one down there, when they kind of come together, they can add up. So if I've got two waves and they have sort of the same phase, meaning that the peaks match the peaks and the troughs match the troughs, then you can get constructive interference and you can get a bigger wave. Alternatively, you can have two waves that destructively interfere, meaning that if the peaks correspond with the troughs and the troughs correspond with the peak, they will basically annihilate each other in a sense, and then you sort of get no wave that results from that. So this is really a unique phenomenon. You don't see this with particles, right? Particles don't hit each other and disappear. So this is really a wave phenomenon, and something that I do want to mention that will come relevant later is that light is a wave. And light can interfere and create these sort of patterns where you have spots of constructive and destructive interference. So brighter places and then darker places, brighter places, darker places. Yeah, so that's an introduction sort of to waves. And you know, this distinction between particles and waves, again, was thought to be extremely clear, but then experiments came in and, of course, ruined the day, and they start muddying the picture. And there started to become an experimental evidence, or experiments started showing that there's a duality between waves and particles, and especially when you start looking at things at a very small scale, right? And this is why physicists did not necessarily realize this until sort of the late 19th and early 20th century, is that you know, big objects tend to either be wave or particle, as we've discussed. So what are these experiments that we will dive a little bit into? Is there's something called the photoelectric effect, which shows that light, which is traditionally thought of as a wave, can actually have particle-like properties. And electrons, which are commonly thought as particles, can have sort of a wave-like behavior, which is very odd. So let's start by discussing the photoelectric effect. So this is actually what got Einstein the Nobel Prize in 1921, the photoelectric effect. He's also well known for general relativity and Brownian motion. He did a lot of things in that, well, that was 1905. But his Nobel Prize actually focused on his contributions to the photoelectric effect. So here's the idea. You have a metal, which is indicated here by this little gray box, and then you shine light at it, and then that light has energy, and that will make electrons shoot off the metal. And there's the classical expectation. Remember how we were talking about how the energy of a wave, it's related to its amplitude, right? Like when you have a tsunami, that has a lot more energy because it's so high compared to just a small little wave that you get when you just tickle the water or something like that. So you would expect that with higher intensity or brighter light, the analog with light is that it's brighter, that you get more energy of the emitted electrons. And when you do the experiment, you see that as a function of the intensity of light, the energy of each electron is the same. So the brighter light does not actually make the electrons have more energy. However, it actually changes the number of emitted electrons. So as the intensity of the light changes, in other words, as you shoot brighter, make it brighter, the number of emitted electrons that you get on your detector starts growing, which indicates that there is sort of packets inside of the light, that as you make it brighter, you actually have more of what are called photons, and each photon is responsible for kicking out each electron. So the photoelectric effect, because basically that it's the number of emitted electrons that was affected by brightness instead of the energy, demonstrates that light, there's particles of light, and those things are called photons. So that's an instance where something that people normally thought of as a wave is actually a particle. Now, there's also this other really crazy thing, which that particles can actually behave like waves. So let's look into that in this so-called electron double slit experiment. So remember how we were discussing how when you shine light through slits, you can have this sort of interference pattern, right? That's sort of one of the distinguishing features of waves. It can constructively and destructively interfere, i.e. have bright and dark spots of light when you shine them through slits. The same thing actually happens in this remarkable experiment where instead of shooting light through the slits, you shoot electrons. And furthermore, what you do is you actually shoot single electrons, right? Because if you shoot multiple electrons at the two slits, you can argue that maybe the electrons are doing some, maybe they're hitting each other or something like that. But here we're trying to focus on just sending single electrons through the slit and trying to show that a single electron actually has wave-like behavior. So when scientists did this experiment, they shoot just single electrons through slits. After a little bit of time, each of these dots represents an electron hitting a detector. You start seeing just spots kind of scattered around. But as you wait longer and longer and longer, you start seeing that there's an interference pattern. In other words, this same bright, dark pattern emerges. From electrons, these are particles, or what were thought to just be particles. And this is evidence that electrons can behave like waves, and very mysteriously, even single electrons can behave like waves. And that sort of led scientists, or confused scientists, I think, for at least a little while, and started, and was really led to this development of this theory called quantum mechanics. Okay, so what are sort of the principles of this theory that we're going to need for tonight? I don't want to, explaining all of it will take a lot of time. But so let's just do some basics here. So one of the key ideas of quantum mechanics is that particles are now described by something called a wave function, meaning that particles are no longer here or there, they're actually sort of everywhere. So there's this concept called a wave function, and that wave function has a value at all points in space. And that value sort of tells you how likely it is to find that particle there. So it sort of gives you a probability distribution of where the particle is, but the particle is neither here nor there anymore. And to actually get the particle to be somewhere, and we'll talk about this a little bit more later, you have to do something that's broadly defined as a measurement, and I'll have something to say about that later. And then sort of another key concept that I want to convey here is that you can think of particles as being in superposition. So what I mean by the word superposition is that it is in many states at a single time, right? So the particle is not only at, let's say this area here, but it's also out in this area here. And I should describe a little bit, sorry, about this picture. So this is a picture of an atom and the wave function of an atom, and essentially the nucleus is here at the center, but the electron is actually not in just orbits around the atom, but is actually located everywhere, basically, at the same time. Okay, so with this wave-like behavior of particles, now particles have the ability to sort of extend through space, which is not something that particles could do in classical physics. And now another feature of quantum mechanics, and I realize that, when the word quantum is actually not something that is too much in the daily vocabulary, but what we mean by quantum is that states now have sort of quantized energy. So quantized meaning that, the energies can only take a discrete set of values, okay? And many properties actually, not just energy, as we'll discuss, can only take a discrete set of values. So how can you sort of intuit that? So one of the classic thought experiments in physics, and also relevant in real physical systems, is this idea of a particle in a box. So if you constrain a particle to be inside of a box, because it can be neither here or there, and has to have a wave function, has to have a spread in space. In this situation, when you constrain it in a box, you force basically the ends of the box to have zero probability. And what that means is that you can only fit certain wavelengths in here in order to satisfy what are called the boundary conditions, the fact that it has to be constrained in this box. And each of these very specific wavelengths will lead to different energies, and this leads to sort of a discrete set of energies or wavelength values, and not every wavelength value is allowed. So that's sort of where the idea of quantum comes from. You now have a discrete set of values. So what else is quantized? And something else that's very, very important is something called spin. So here I'll present another experiment, and if you haven't really gotten the gist yet, quantum mechanics is a very experimental science, or it has a very strong experimental basis. And this experiment is something called the Stern-Gerlach experiment. So in this experiment, you have a particle source. I think one of the early ones was done with silver atoms. And you shoot them through a magnetic field, or magnetic field gradient in particular, and you look at the deflection of the particle afterwards. And what is sort of interesting here is that you, instead of getting a wide range of deflections, you in fact only get two possible deflections. And one of these became named spin up, and the other one became named spin down. So with this experiment, you see sort of another quantization where you can only take two values. You can't be anywhere along this sort of region of space. And that led to the discovery of the concept of spin. So there's one type of particle that tends to go up, and one type of particle that tends to go down. Now, what's kind of interesting is if you take this sort of particle that goes up, and you ask what happens when you put it through the detector again, it actually stays up. It doesn't sort of make a different choice. But the particles beforehand, sort of had this ability to either go up or down. But after a particle is already up, it will now stay up. And this is the concept of collapsing the state after measurement. So essentially, after the particle has decided to go up, then it has become the up state, so that when you repeat the experiment, it will stay in the up state. And this is something also sort of a weird feature of quantum mechanics. And just to review that one more time, so at the beginning of the experiment, I would argue that the particles are in a superposition. They are in either up or down, or both at the same time. Now when they go through the magnet, they sort of make a choice between going up and down, but once they have made that choice, once that measurement has occurred, then the particle will stay up unless perturbed in some other way. Okay, so now why do we care about this? And we will get to an example of this in your everyday life. But before we get there, I want to give some interpretation for what we're seeing, because I think this is something that, this aspect of quantum mechanics, the idea of being in superpositions, is something that has sort of entered the public domain, and you may have seen this in this example of Schrödinger's cat. So here's a famous thought experiment from Erwin Schrödinger, one of the fathers of quantum mechanics. And he had this thought experiment where if you place a cat in a box with poison, and that poison is then released at some point in time, is the cat in a superposition of being dead or alive? So you may have seen, t-shirts about whether the cat is dead or alive or not, but that's the experiment. You put a cat in a box, you put it with some poison, but you don't know when the poison will release, and then you ask the question, basically, what is actually happening? Is this quantum mechanical? And people usually use this thought experiment to explain superposition, which my personal opinion is a disservice. And basically, they will say that before you look at the box, the cat may be in a superposition, but once you make the so-called measurement, then the cat is either dead or alive. It can only take these two values. You will not see a cat that is dead and alive at the same time. You will not see a ghost. But this, is a good thought experiment to illustrate the concept of measurement. I think that's valid. The idea that the system can be sort of in an unknown state before you observe it, but it leaves many open-ended questions that really spooked people. You can ask the question of when did the superposition actually collapse, if it were actually in a superposition. Like if the cat were both dead or alive at the same time, when did it exactly die, if you look at it and you see that it's dead? I would personally argue that it's very human-centric to say that it died when you looked at it, because there are certainly other things in the world that could tell that the cat is dead or not, right? So in some sense, this thought experiment leads to these very deep questions. And this is, by the way, why Schrödinger introduced this thought experiment. It was not introduced to sort of just explain measurement or to claim that cats can be dead or alive at the same time. It's really to bring this fundamental problem of measurement, which is, what does it mean to actually measure something? Like, what does it mean when you actually look? And then there's, of course, the question of can a cat, which is very macroscopic, actually be in a superposition? So these are sort of the questions that are raised by this thought experiment. And I want to sort of, parry the question, or basically try to not get caught up in these details, because I want to emphasize, hopefully through the experiments that I described to you, that quantum mechanics is ultimately an experimental science, meaning that its predictions have been verified, and you can make these predictions without trying to make super serious interpretations. And these predictions can be made independent of the interpretation. That is sort of the mathematical framework that quantum mechanics gives to you. And this is, I think, quite valid. I think Albert Einstein was extremely spooked by this idea, and he made this famous quote that I, at any rate, am convinced that God does not throw dice. And I would argue we don't need to worry about a God, and we don't need to worry about whether God is throwing dice or not. The point is that quantum mechanics can make experimental predictions, and they can be verified, and that verification can be done independent of exactly how you choose to interpret it. Okay. So, and now I'm telling you that it can make predictions and be verified, and I will say that not everyone, hopefully not every one of you, has had some experience with quantum mechanics in the medical field. And what I'm talking about here is MRI. If you've ever had an MRI image taken of you, this is a quantum mechanical effect. Remember those spins that we were talking about earlier, this concept that something can be up or down, basically? That is the underlying principle behind how MRI works. And MRI basically induces these tiny spins, and it's called spin because you can think of it as kind of a magnet or something like that, basically something that is rotating. And the MRI machine uses magnetic fields to induce these tiny spins to rotate, and it measures that. And without quantum mechanics, that would not be possible. The concept of spin would not exist. And using this technique, you can do crazy things like look at multiple sclerosis lesions in the brain. It looks terrible. I hope that has not happened to you. But with this sort of quantum mechanical effect, you can see things that you could not see necessarily with your eyes. Okay, so basically that's sort of a whirlwind tour of quantum mechanics, and then we'll see how you can now use this or use these basic concepts of superposition and measurement and all this stuff that we were discussing, and we can see how we can use that to compute things. So that will be the next part of the talk, and I think we'll take any questions here.
Fantastic, that was a great introduction. So we can now take questions from the audience, and as a reminder, if you're watching on our YouTube live stream, feel free to drop any questions that you have in the chat, and we'll relay those to our speaker. So do we have any questions from the audience?
So I guess you didn't want to get too caught up in the details, but do we have any advances in our understanding of what a measurement is since the early 20th century? I mean, I think all of the examples you gave were pretty, like over 100 or close to 100 years old now. So is there like a modern conception of what the measurement is?
Yeah, so I guess I'll repeat the question in case it didn't come through online. So the question was basically, have there been any advances in really what a measurement is over the last 100 years? And I'll say it's an extremely complex subject, and people are studying it, and I've seen papers of people describe weak measurements, the idea that there is even a spectrum of measurements. And what I will say to it is sort of what I had said in the philosophical part of this, is that I choose not to really worry that much about that. In the sense that it is, you know, within the framework that I know, a measurement is something, and it might be able to make predictions in my experiment. And that is sort of what I care about most at the end of the day. But maybe I will shed a little bit of something of just my personal taste. Measurement is something that cannot be explained by so-called something in quantum mechanics called unitary dynamics. In quantum mechanics, there's this idea that when you change something, you can always go back. And measurement kind of fundamentally violates that because it's probabilistic. You know, you have a probability of being there or there. And some people attribute it to the fact that you don't have complete knowledge of the system. So I don't know if I want to go on the record of this, because I don't know if things will change in many, many years. But my personal feeling is that if you knew about the measurement device and exactly what state it was in, maybe the measurement result would be deterministic. But I'm not 100% sure.
Do you have any other questions from the audience? I had a question. You kind of mentioned this whenever you were talking about Trimmer's cat. But how small is small? How small does it have to be to have a quantum fix?
Yeah, so the question is basically how small does something need to be quantum? And That's an extremely good question. I think without getting too much into it, I will just say sort of electrons tend to behave quantum mechanically, so it kind of has to be on that scale where it's near like an atom or a molecule. But people are actually making advances with macroscopic objects being quantum, and we'll discuss that actually. The way some quantum computers function now is they are macroscopic objects, and the way they make them behave quantum is also going very cold. I'll say one thing about that. What is sort of important is, I mentioned this quantization of energies, basically, how you can only have some set of energies allowed. And for something to be quantum, you need to have the ability to pick out one of those energies or two of those energies to really worry about. And that's not something that, rolling a ball will satisfy. Rolling a ball will be in a bunch of different states at the same time. You don't need to worry about that. So that's where the ultracold comes in. And I will use this time to actually advertise a Science in the News talk, I think from 2 years ago. It's in the link of this YouTube video, and I think also on this handout where other people from my lab actually talked about making things ultra cold in order to make them quantum.
Do we have any other questions from the audience or on our YouTube? All right. If not, we'll take a 2-minute break, and we'll be back here at 7:29.
All right, it's been 2 minutes. Now we're back for the second part of the talk.
Okay, so we had just discussed sort of the salient features of quantum mechanics. As a reminder, basically waves can behave like particles, particles can behave like waves, and what that means is that particles can now be in superpositions, can be in multiple states at one time, right? Can be like a wave, can be in multiple places at one time, for instance. Now, how can we use this feature to actually do some computation, to do something useful? Okay, so before we get to that, let's discuss a little bit about how classical computers work at a very high level. And classical here again means the computers that are sitting in your desk, something that uses classical physics, which is actually only half true, but anyway. Classical computers use something called bits, and this is a very beautiful abstraction where you basically have two states, 0 and 1, and that's how you do all the computation. You abstract everything into zeros and ones. And sort of a physical, what happens in your computer is this actually runs on electricity, where you have a high voltage which represents 1 and a low voltage which represents 0. Now, what do you mean? Like, how do you use zeros and ones to compute? Well, once you have zeros and ones, you can start stringing them together to represent numbers. You can give an interpretation to 0, 0 and call that 0. You can interpret 0, 1 as 1, 1, 0 as 2, and 1, 1 as 3. And now you can imagine that now you have numbers. Maybe you can start doing arithmetic on numbers. You can start figuring out how much you have to pay in tax, for instance. But if you broaden your mind and you have zeros and ones, right, you don't have to stick with number representations, right? You can even decide that if I had a set of zeros and ones, that a particular pattern of those can represent A, B, C, D, E, F, G, H, I, J, and now you have starting to have the representation of letters, right? And then from there you can go further and further, right? Instead of just representing letters, you can now put these things together to what computer scientists might call structures, and you might be able to store, for instance, the red, green, and blue value of a pixel on your monitor or something like that. So once you have this abstract concept of zeros and ones, you can now put things together and actually get numbers and get other fancier things. And I will say that modern computers, when you buy RAM or something like that, or you buy a computer, you might figure out hard drive size. This is what they're talking about. And modern computers easily contain trillions of these bits to both store and process information. Now, these bits, if on their own they don't really do anything, you have to manipulate them. And you manipulate them through something called gates. So you can have something called an AND gate or an OR gate. And the idea here is basically you have two inputs and an output, and you can calculate something called A and B or A or B. So if A is, let's say, false is a 0 and B is also false, then A and B will remain 0 and A or B will also be 0. And another example would be, let's say, this third row here. So if A were 0 and B were 1, then A and B is not true. In other words, not both A and B are both 1, but A or B is true and is a 1. So you can start using these logical gates. To manipulate these zeros and ones. And now you can kind of see you're on your way to things like arithmetic and things like changing values on your monitor screen, right? If your pixel suddenly becomes more red or something like that, then that is sort of a manipulation of the zeros and ones behind the red value on your computer screen. So bits can be manipulated through these logical gates, and these combinations of these can be put together to create functions and algorithms to do useful things, right? So, such as that changing your pixel on the monitor example. And these gates are now performed on chips that look like this, and just to give you a sense of scale, it's roughly on the size of like a quarter, not that much bigger than that. And this can run billions of these gates per second. Like, that's how good we have gotten to manipulating zeros and ones. So what's special with quantum? What's special with quantum is now you have this idea called a quantum bit, a qubit. And a quantum bit, the key new feature of quantum, which we had discussed in the first part, was that things can be in superpositions, meaning it can be in multiple states at one time. And how does that manifest itself in computing? Well, that means that you can be in 0 and 1 at the same time instead of being 0 or 1. So what do I mean by that? So let's imagine some atom. So this is one way to realize a quantum computer. So you have an atom with a nucleus, and then you have an electron which could be in these two possible orbits. And one of these orbits we would call 0, signified by the red dot. And then there might be a different state called 1, which is this green dot. But the cool thing about quantum is that you can actually be in both of them at the same time. There is a state that is allowed that is called 0 plus 1. I will make a note that I'm using this fancy notation here. That's something called a ket. But the only thing that matters here is I want to just make sure that you don't add this and say that 0 plus 1 is 1, and I'm just trying to write 1. No, this is the state 0 plus the state 1. So that's why I put these little things there. And that's sort of one qubit. It can be in both 0 and 1 at the same time. But how about multiple qubits? And yes, you can have multiple qubits. So with 2 qubits, if you can calculate and figure out how many different states you have, and there are 4 different states, you can either have both 0, 0, 1, 1, 0, or 1, 1. Those are the 4 possible configurations of 0 and 1 when you have 2 of these objects. And very importantly, you can be in all 4 of these at the same time, right? That's sort of the beauty of superposition. And things start getting complicated, right? Once you have 3 qubits, now there are 8 states. I can still fit this on this slide, right? You can go through all the combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. But once you have 100 qubits, which by the way is still much smaller than like the trillions of bits that are on your computer, you run into having 10 to the 30 states at this point. It be impossible for me to write on this slide. And just to give you a scale of what 10 to the 30 means, right? That is more than the number of stars in the universe. So if every star represented one of these states, you would run out of stars. And this really gets ridiculous. At some point, and not at a very big number, you will have more states than the number of atoms in the universe. And that is problematic, I think. So what that means is that quantum systems contain and store far more information than classical states. So one quantum system with just 100 two-level quantum systems, somehow nature has put 10 to the 30 pieces of information in it, right? Namely the probability of being in all of these states, because it can be in all of them at the same time. And this makes, as you can imagine, studying quantum systems extremely difficult. Imagine you were taking a class and somebody told you to write down these 10 to the 30 states, you will never finish, right? So maybe you can put it on a computer, but then you realize this number is more than the number of stars in the universe, and that makes studying quantum computers studying quantum systems extremely difficult. But I argue there's sort of a flip side to this. It makes studying quantum systems difficult, but also it allows these systems to be used as a resource for computation, right? There's a lot of information in here. The question is, can you actually leverage that for something useful? So it's really a double-edged sword, I would say. It makes these things very hard to study, but that's also exactly where their potential comes from. So so now that we have qubits, we have these zeros and ones. You can be in multiple of these zeros and ones at the same time. We need to be able to manipulate them, so there is an analog to the and or gates that we were talking about classically. Those are just called quantum gates, for lack of creativity, where qubits are manipulated from one state to another state. So there are, for instance, some gate called a Hadamard gate, for example, which converts 0 into this particular superposition of 0 and 1, and converts 1 into this other superposition of 0 and 1. This is, by the way, has no classical equivalent. There's no classical way of being both 0 and 1 at the same time. You can't have a high and low voltage at the same time. So this is really something truly quantum. Something that's perhaps a little bit less quantum, but still quantum, is a controlled NOT gate. So here is a 2-qubit gate, which converts 0, 0 into 0, 0. So the first qubit is called the control qubit. The second one is called the target. When the control is a 1, then it will flip the target. So 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. 1, 0, the 1 is the control bit, so that means we're supposed to flip the 0. So 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. This is another valid sort of gate. 1-qubit gates require you, so now if we want to get a little bit practical, which we'll get into the third part of the talk, we will need some way to manipulate the quantum state of the system. This is one requirement. And 2-qubit gates require some sort of interaction between the qubits, right? You need some way for the target qubit to know what the control qubit is, right? If the 2 qubits didn't care about each other, then there's no way you can perform this kind of conditional sort of transformation. Okay, and that's sort of setting the framework for the third part of the talk. But now that you have these qubits and you're able to manipulate them, why is your password in danger, right? Back to the title of our talk. So there are quantum algorithms out there that can do things faster than any classical computer can. And I want to present a few of these examples without getting too deep into the details. So one of these is a really cool algorithm called Grover's search algorithm. Here's the problem. You want to find an object. You have a set of objects, and you want to find one particular object. Okay. For example, you have a bunch of boxes, and you have blue balls and one red ball in them, and you want to figure out which box contains the red ball. Okay. Classically, what you have to do, if I gave you a bunch of boxes and balls, is you'd literally have to check every single box and say, okay, is this ball red? Is this ball red? Is this ball red? Is this ball red? And on average, you probably have to check at least half of them, right, before you actually find it. But quantum mechanically, it turns out that you don't need to search anywhere near to half of them. Okay, and I'll show you how that works. But before we get to exactly how that works, I do want to point out something, and that is that quantum algorithms, may be able to perform, operations on, all these different states in parallel. In other words, if you are able to store the fact that you're in all these different states at the same time, 0, 0, 0, 1, 1, 0, 1, 1, you might be able to manipulate them at the same time, which seems really powerful. But the problem is that each computation will only yield a single measurement result. At the end of the day, you still have to measure and get an answer out of it. So that means you have to be very clever, and you have to use what is called, or what we discussed before, interference to increase the probability of the correct answer. So let me demonstrate how that works. So this is how many quantum algorithms work. You start by sort of creating an equal superposition of all of the objects, if you will, at once, right? And here's our special red object. Pretend that the red object is in box number 13 here. And you start in this sort of state, but then if you decide to make a measurement now, right, then it's kind of useless because you can be in any one of these and they all have equal probability. The height of this bar tells you how likely it is to actually find the quantum state in that particular state, the quantum system in that particular state. But when you apply Grover's algorithm, you do this kind of special interference where your quantum gates know where the right answer is, right? We assume that your quantum algorithm knows what red is, and it's somehow able to check all these boxes at the same time. And when you start applying the rules of this algorithm, you can actually grow the probability of the correct one, and grow it more, and grow it more, and grow it more. Until you're in a situation where basically this is the only component left in your quantum system, where basically if you make a measurement now, you will find the red particle in box number 13. It will tell you that it's in box number 13. Another way to think about it, if we want to think about it using the interference that I discussed earlier, the algorithm has come up with a way to make sure that box number 13 completely constructively interferes and all the other boxes destructively interfere. So they're all gone. And then you make the measurement. And notice how many times I had to do this. I only had to do this 4 times. Nowhere close to, 16 times in these 32 boxes. And this is sort of how a lot of these algorithms work. You start with a uniform superposition where you have all the possibilities allowed, and then you do some sort of interference to boost up the correct answer. And you know that it's the correct answer because you can check all of them at the same time. That's what's special about quantum mechanics, right? So maybe just to reiterate one more time, if you had a classical computer and you were doing something like this, you would have to check them one by one, right? Your classical bits can only be in one of these 32 states at the same time, but quantum mechanically you can be in all 32 at the same time. That's sort of where quantum mechanical advantage comes from. So let's get into the title of the talk. Basically, is your password in danger? And this is something that brought shockwaves into the community, and this is something called Shor's algorithm. And I think I was at a talk where people were talking about sort of the history of developments in quantum algorithms. And I think Peter Shor himself, to try to convince people, to try to get governments to invest in quantum, they had to come up with something useful. And it's not easy to come up with useful things in quantum mechanics, or in this quantum computing, because these algorithms are very non-intuitive in a way, right? Like I just broadly said, you have to somehow interfere these things correctly, but it's not at all obvious just from the way I said that how you would actually do it, right? So Peter Shor actually sat down and tried to come up with something that will actually scare people, something that will actually be useful. And he came up with this thing called Shor's algorithm. Okay, so what sort of problem does Shor's algorithm tackle? It tackles the problem of encryption. So what do I mean by encryption? So when you want to communicate with somebody, right, you may want to tell secrets, right? And it's hard to tell secrets online because when you're online and you're passing information around, people can intercept it and look at what you've been doing, right? If your internet service provider may want to know where you've been, if the FBI wants to know where you've been, they usually can tell. So we need some way to prevent eavesdroppers from coming into play. And that process is usually called encryption. So what you do is you sort of change your information in a way, but you change your information in an agreed upon way so that only the listener of the information will know what you're trying to say. And one example of this, the simplest example I can think of, is we can encrypt, for instance, the word bank with the word cabal. How did I get cabal from bank? Well, I agreed that B should become C. You advance B by 1, so B goes to C, A goes to B, N goes to O, and K goes to L. Now, if I told somebody cabal and they knew about this technique, then they will be able to say, oh, you actually meant bank. But if you did not know this transformation, you would not be able to tell that I was trying to give you my bank account number or something like that. So that's just the general idea of encryption. It's way more sophisticated than that, right? You can probably think about ways where you can crack this, right? You can probably just, check, is it 1 letter behind, 2 letters behind, 3 letters behind, you probably can figure it out. And these days there's something called RSA encryption. It's way more complicated. I'm not going to explain exactly how it works, and to be honest, I don't really know exactly how it works. But the general idea is that you have public and private keys. You can think of it as sort of 2 pieces that will fit together. And only when you have these 2 pieces that fit together can you actually decode what the actual message is. So the way that this usually works is that you have what's called a public key that everybody knows about, and you have your own private key, okay? And basically, if Alice wants Bob to send a message, Alice will tell Bob, please use my public key, which is accessible information to everybody, and use that to encrypt your message, right? Take your message and manipulate it using my public key, okay? But only I have the private key. So when that information comes to me and me only, then I can decode and figure out what it is, okay? Now, how would you break this? Well, if public and private keys were just shapes and you knew they had to become a square, then it would be very easy to sort of break this. But in real RSA encryption, what's used, the most predominant form of encryption used today, there is a problem that you have to solve, basically to figure out the triangle to this Pac-Man, I guess. You have to solve what's called the factoring problem, which is the problem where you're given some large number n, which is the product of 2 prime numbers, and you have to figure out what those prime numbers are. And the safety of Alice's private key relies on the difficulty of this problem. And this problem is known to be extremely difficult to solve and very easy to verify. Okay, so on classical computers, it's known that this problem becomes exponentially more difficult as the integer gets large, as n gets large. And Shor's algorithm, which is a quantum algorithm, only gets more difficult in what's called a polynomial way. So let me demonstrate exactly what I mean by that, by this graph here. So here we're looking at the number of operations it takes to crack this code to determine P and Q, to steal Alice's bank account number, and the number of operations you need as a function of how big the number n is. And for the classical algorithm, you can see once the number is like around 10,000, it will take something like 10 to the 16, 10 to the 17 operations to actually figure that out. Whereas the quantum algorithm, it stays underneath 10 to the 4. And just to give you a sense of scale on how big 10 to the 17 is, current computers maybe run about 1 billion operations per second. And it would take, at least in a naive calculation, it would take about a year to sort of crack this at 10,000. Okay. So this is why this is used as encryption, right? It's supposed to be a hard problem to solve. So because it's a hard problem to solve, your password is safe, your private key will never be revealed unless you reveal it yourself. But with the quantum computer, perhaps your password will be in danger because you can crack it way sooner than what you could on a classical computer. So that's sort of why your password might be in danger, and we'll see in the third part of the talk. Stay tuned for whether you actually need to be worried or not. All right, I want to branch off to one other thing that kind of is a theme of that we had discussed earlier, which is this concept of quantum simulation. So these quantum systems contain a ridiculous amount of information. Remember, you need 10 to the 30 numbers to characterize a single, a 100 qubit system if you only have 100 qubits. So how do we as scientists or anybody in the community, how do we try to study these quantum systems? And this is very, very difficult with the classical computer because of what I had just mentioned. So there's this idea of quantum simulation, which is attributed to Richard Feynman. And he had this great quote, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." So in other words, instead of trying to represent this quantum state that you're trying to study with all these numbers on a classical computer, use a quantum system itself. That's the idea, okay? So for instance, if you want to study, and this is one of the big motivations of how everybody gets money in this field, is they harken to this high temperature superconductivity. This is a quantum mechanical effect. So superconductivity, what that means is that you have a conductor that conducts electricity, but has literally zero resistance. That's the idea of a superconductor. And this is extremely relevant in society, because if we had a superconductor, then we can transmit electricity without any loss. And electrical transmission right now has a lot of loss. Like, we waste a lot of energy this way. So this is perhaps a way to solve our energy problems. If we can replace everything on the grid, with superconductors instead of normal conductors. The main problem is that these superconductors tend to be very cold. They need to be at very low temperatures to actually have zero resistance. And people are interested in trying to figure out how we can potentially make a high temperature superconductor to actually work, transmitting electricity on our grid. This problem is extremely hard. You're trying to simulate all the atoms inside of this solid. So we can study it instead with another quantum system, but a quantum system that we can control. And here I showed a picture from our lab where we have individually trapped atoms micrometers apart. And we can use this to study this system. That's the idea behind quantum simulation. This is a quantum mechanical effect. This is a quantum system that we can control. And we try to manipulate this and see if we can see features of superconductivity in this controlled system. That's the idea behind quantum simulation. Okay, and that is the second part of my talk, and we will discuss where we are as far as real-world implementation in the third part.
Great, thanks so much. So again, as another reminder, if you're watching on the YouTube feed and you have any questions, feel free to type those in the chat, and then we'll relay them. Does anyone in the audience have any questions?
Hi, thanks for your talk. I was wondering, how many qubits do we need for it to become actually commercial, and what's the limitations on getting to that point?
Yeah, so the question is, how many qubits do we actually need to make this commercial, and what are the limitations? That's basically the entire third part of the talk, so we will get to that. So wait, be patient.
So you said that 100 qubits have 10 to the 30 bits of information, but my hard drive on my computer has a terabyte of storage, so that's 10 to the 12 bits of information. So does that mean that I'll be able to replace my hard drive with a 20 qubit quantum computer?
Yeah, that's an extremely good question. So the question is basically, when you have 100 qubits, you have 10 to the 30 sort of pieces of information, right? The coefficients of all of these states that you can be in. And does that mean that I can replace my terabyte hard drive with just a few qubits? And I would say broadly the answer to that is no. All that information is there. And all that information is relevant, for instance, in the science of superconductors, meaning that in order for a superconductor to work, all those pieces of information have to behave in the right way. But when it comes to making it useful for computation, not all 10 to the 30 of those are going to be useful, right? You still need to find a way to interfere it, and perhaps the more prominent constraint is that when you only have, let's say, 10 or 100 qubits, you're limited in what you can represent, right? It's sort of the fundamental, even in that Grover search, it was imperative that we were able to represent 32 distinct numbers, right? You have 32 different, like each bit string can represent 32 numbers. And that means that your terabyte hard drive can represent 2 to the terabyte of things, whereas your quantum computer cannot represent that many things. Not every one of these coefficients can be used at the same time. Yeah.
Do you have any other questions?
You kind of said this is a throwaway at the start of this part, but do classical computers have quantum mechanics? I mean, they must have quantum mechanics involved, but you kind of made a throwaway. Could you kind of explain that a little bit?
Yeah, so caught me saying something that I just wanted to put in there. So the question is, do classical computers take advantage of quantum mechanics? I'll just tell a brief story. This is harkening back to my qualifying exam because I had originally had something like this on my qualifying exam slide, and my lab mate told me to remove it because I did not want to get into this sort of discussion. So the transistors, I believe the fundamental principle of how transistors work, now people should fact check this, always fact check what you hear on YouTube. I believe they rely on, they do rely on quantum mechanical effects, these p-n junctions and things like this. I believe there's some quantum mechanics in there, or there is some quantum mechanical description that you need to actually explain how transistors work. Transistors are the fundamental unit in your computer. And one other thing is that quantum mechanics is actually limiting how to make classical computers better. The way that classical computers have become better is you make these transistors, which are these fundamental units, smaller. And they're being made so small now that quantum mechanical effects are starting to come into play. And that is actually one of the limitations for how many transistors you can pack on a chip. The processes now that these companies do are like down to like 5 nanometers, 3 nanometers. You're getting to the point where quantum mechanics is relevant. So it might stop classical computers actually from getting better to some extent.
If we have no further questions for this part, then I guess in the interest of time, if it's all right with everybody here, we can just continue straight on to the third part.
Sounds good? Yeah. Okay, so just to answer the question from the audience, I know you're all excited to hear about this. What is sort of the current state of the art, and what's sort of the, how do we, where are we right now, basically? Are we anywhere close to worrying about your password? Okay, so let's get to the very practical question of how you build a quantum computer. Okay, so these are a little bit of what quantum computers look like these days, and we'll discuss a little bit about how these work. So here's a quantum computer from IBM. For scale, this is sort of like the size of a room. It's kind of big. It's got shiny stuff. Here's another quantum computer from the National NIST, is the National Institute of Science and Technology, or something like that. Yes, you can look that up. NIST. It's government agency in the U.S. And this is on the size of, it's roughly on the scale of one of these chips. So this is sort of another approach where you're not in a room, but now you're kind of on a chip. And really we need to ask the question of, and which has kind of been asked a little bit by the audience, of what can be a qubit? Like, can this laser pointer that I'm holding, can that be a qubit? How do we control these qubits? We touched upon that briefly with gates, right? You're gonna have to manipulate these. And then how do we scale up the number of qubits and transport quantum information? Going to the question from the audience about how many do you need, and is it easy to get many, right? So these are sort of the questions that we have to answer to figure out, how to reasonably answer the question of whether you should be worried about your password. Okay, so what can be a qubit? In short, the qubit needs to be a quantum system. It's a quantum bit, and it needs to behave quantum mechanically. Okay? This is sort of a tautological definition, so let me just dive into a few examples. So one example is people have been using ultracold individual atoms and ions. People have been using what are called superconducting quantum circuits. Individual photons of light, so sort of back to the beginning of the whole talk where we were talking about how light is actually composed of particles. These particles can be qubits. And also, another thing, going back to the MRI example, you can also use these little spins inside your body or inside any molecule, these nuclear spins in a molecule. Now, these look like 4 very, very distinct things, but what do they have in common? Well, they all have this concept of isolation from the environment. Basically, when you have superpositions, when you're both here and there, it's very hard to be both here and there at the same time. And you need to really protect that, because that is really what's necessary, for instance, to make that Grover's algorithm work, where we saw sort of this very nice orchestrated constructive and destructive interference to sort of extend the probability of of finding the correct answer. So we really need isolation from the environment to protect these fragile superposition. Individual atoms and ions, nicely isolated, because they're individual. You have one here, one there, one there, one there, like that little smiley face I showed earlier, right? Very isolated, okay? And for scale, a table in your house has 10 to the 23 of these atoms, right? Superconducting quantum circuits, you need them to be superconducting because resistance is bad, right? Having resistance means that electricity is bumping into each other, it's heating stuff up. That's bad. We need something superconducting to not have any sort of collisions, basically, that will destroy these fragile superpositions. Individual photons are great. Photons of light are very isolated. They will just go places, right? When I shoot this laser pointer, that light is just on its way, okay? So very isolated from things. It's not just bending randomly and hitting things. And lastly, the nuclear spins in a molecule are also very well isolated in the sense that these tiny magnets don't really talk that much with each other. And that's one reason why MRI is so great, right? MRI is so great because you can really hone in on this while, ignoring all the fluff, ignoring all the extra stuff around. You can kind of key in on these individual spins. Okay, so the key thing about, what makes a qubit is you really need to be quantum mechanical, and you have to have the ability to be in these fragile superpositions. Okay, and that is sort of also why things need to be cold, because if you had energy around, you can potentially also ruin your fragile superposition. Okay, so the next ingredient is control. So how do we control these things? With ultra-cold individual atoms or ions, these tend to be controlled by lasers. You can use lasers to change the state of the atom to promote it from one orbit to the other. For superconducting quantum circuits, you use a microwave, actually. So this is a household microwave. It shoots out radiation, and that radiation tends to be the radiation that you can then put into these circuits and manipulate their states. With photons, you have everything that you have accessible in optics, and you might even have this in your home. I think this is a really cool picture. If you ever heard of Verizon Fios or fiber optic internet, it's photons. It's light, basically. So if you snip one of these fiber optic cables, you can actually see light coming out, right? This is sort of the difference between fiber optics and sort of like classical transmission lines, right? Your fiber optic communication actually is communication via the light and not electricity. And I'll just briefly mention that this is what makes this platform, by the way, the most promising for actually transporting quantum information, right? You can actually get that from one place to another by using this nice technology of fiber optic cables, which are really going all over the world right now. For these nuclear spins and molecule, we already sort of talked about how you manipulate these. If you've got an MRI machine, or in this case an NMR machine, very similar but more used for scientists, you can use that to sort of make your spins do stuff for you, basically, make them rotate in some way. Okay, how about this concept of 2 qubit gates? So this is how you just change from one state to another, right? How you can actually manipulate your qubits. So, and I guess I didn't quite mention how optics, but this is how you transport it, but then you can use beam splitters, things to deflect light, for instance, and use all kinds of optics to manipulate them. So this is what's sort of represented by this picture, including fiber optics. So for 2 qubit gates and scaling up, so 2 qubit gates, remember, is sort of that control NOT gate that we saw earlier, where you have this sort of conditioning. The 2 qubits have to know about each other in some way. And then one qubit has to behave because it knows about what the other qubit is doing. So there needs to be some sort of interaction. So how do 2 qubit gates work? With individual atoms or ions, these are, in some sense, composed of fundamental particles that contain charge, which means that they can interact via electric forces. And for scaling these up, I showed the smiley face earlier of atoms in our lab. You can sort of create arrays, a bunch of these traps, and have a lot of atoms. Superconducting quantum circuits interact through electrical connectivity. These are literally circuits with superconducting components. And because they're circuits, you can hook them together and shoot microwaves at them and have them interact basically through the fact that they're electrically connected to each other. And they're very nice, or at least the advocates of this technology will say it's great because you can take advantage of existing fabrication techniques. So the fabrication techniques that you use to make those processors that we were looking at earlier, some of those techniques can also be used for fabricating these superconducting quantum circuits. Photons, the hard thing about photons is interactions are difficult. So if you want a photonic quantum computer, photons just simply don't care about each other. They kind of just go on their way, right? Individual photons will not care that there's a photon nearby, so it's actually very difficult to engineer interactions. But the scaling is fantastic. Laser sources contain plenty of photons to work with. Okay, this laser pointer that I have here has many, many photons in it that you can use. Each one of those can be a qubit if you can somehow harness this. For nuclear spins in a molecule, briefly sort of mentioned this with the Stern-Gerlach experiment. Spins there's something magnetic about spins, so they can interact basically via magnetic forces, which are not very, very strong, but they can still interact. And then for scaling up to get more of these spins, so each one of these is a qubit, you just need a bigger molecule, basically, to get more qubits. So that's sort of how each of these platforms sort of compare as far as interactions and scaling up. So what is the current state of the art on these platforms? So the question is, so first to answer the question from the audience, how many qubits do you actually need to factor a 1024-bit number? This is a number that is on the order of 2 to the 1024, not just 1024. And it turns out you actually need about 2050 qubits to do that. Okay, not a ridiculously high number, actually. And what is sort of the state of the art these days? So companies are in on this, startups are in on this. So IBM has some superconducting circuits, and they have about 433 qubits, and they give it this fancy name called Osprey. I don't know, what is an osprey? Is it a bird? Sounds like a bird. Then you've got Google, which has 53 qubits, and also in this superconducting circuit format that's called Sycamore. IonQ is a startup, and they're using trapped ions, so the first thing on that list of 4. And they've got 32 on a platform called Forte. QEra is a neutral atom-based quantum computer, like that smiley face. They have about 256 in something called Aquila, I don't know. And Xanadu, which I think is a Canadian company, is doing photonic quantum computing. They have about 216, and I think that's the coolest name, in Borealis is what they call that one. And there are many, many others. You can make a search for this. People are really coming online, but this is sort of the number we're talking about, the hundreds. Wait, but we only need 2,000 for our passwords to be in danger. This is looking bad, right? We're getting pretty close. But there's a catch. The number of operations you need to actually do this is 4.8 trillion. You only need 2050 qubits, but you need to perform 4.8 trillion operations. Okay, and this is already much smaller than that graph that we were looking at earlier for a classical computer, right? Classical computer, we're up to trillions of trillions of trillions of operations. But with this quantum computer, you still need 4.8 trillion operations. And so imagine that you had error rates, right? Because when you're trying to manipulate these things, you can make a mistake, right? Ones can become zeros. If you have error rates of 1 in a trillion, the algorithm will only succeed 0.8% of the time. You need to try quite a few times to actually get sort of your password revealed. And and this is error rates of 1 in a trillion. So 1 in a trillion, so 1 in 100 is 1%. 1 in a trillion is 0.0000, many zeros, 1%. And our current error rates is 0.5%, which is, as scientists say, orders of magnitude higher than what you actually need. So I would say we are a bit far from actually having to worry about this, because with this sort of error rate, forget about that password scheme ever working. It will basically never work, because even if you had the 2050 qubits. Okay, so are we not worried at all? So in the sense of, from a security standpoint, maybe this is good, we're not worried about this. But from a sort of an innovation perspective, this is kind of depressing, right? The fact that we are so far away. So what are sort of the pathways forward here? The pathway forward is, this is being debated. There are potentially, people will probably come up with other ways, but the most prominent right now seems to be this idea called error correction. So gate error rates are so high, just the 0.5% is quite high, because quantum states are fragile. Once again, these superpositions really, really need to be protected. But classical bits can also be fragile, right? Ones can also, like you have a power outage, all your ones become zeros. Okay, that may not be a great example, but errors can happen, right? Ones can become zeros, zeros can become ones. And one thing that I will say is that classical computers, one way in which they're protected from errors is that they are fundamentally digital. What I mean is a high voltage is 1, a low voltage is 0. okay? What does high mean? High just means higher than some number, right? For, I think, TTL, it's something like 0.8 volts or something like that. So as long as you're higher than that, it doesn't quite matter if you're 1.2 volts or 1.6 volts, you know, you're still considered a 1. Quantum computers do not have that luxury. The number, you know, the probabilities of each of these states, all of them have to conspire in exactly the right way to make that red bar pop up, right, in the Grover's algorithm slide. So in some sense, quantum computers are going to be fundamentally more vulnerable because they are fundamentally not digital in some way. But this is not game over. Classical computers, you know, even the fact that they're not digital, they still need some sort of protection, especially for communication across networks. Voltages can just drop, right? Energy can be lost. And what you do is you typically introduce repetition. So what you do is instead of saying 1, if you want to tell somebody the number 1, you send a bunch of 1s. You say 1, 1, 1, 1, 1, 1. Okay, and as long as most of them are 1, if you have one error, you'll still see most of them are 1, and you're just like, okay, well, you probably meant 1 because, you know, because there are so many 1s. So essentially, there's this trade-off between the number of qubits and the error rate, meaning that if you had more bits, if you had access to more bits, you can reduce error rates by doing something called error correction, by protecting your information, by repeating it over and over again. So what I'm showing you here is sort of one of the most promising sort of potential pathways to this in quantum computers is something called the surface code. Suffice it to say that each of these blue and orange dots are qubits, but the whole thing here only represents basically 1 qubit. So I'm using all of these qubits to represent just 1. I'm building in redundancy, and that's how I protect my system. But now this makes that 2050 number extremely large, right? Meaning that if I needed 2050 originally, now I need 2050 times however many stuff I've got here. And this is actually nowhere close to being enough qubits to actually have the error protection that you need with this 0.5% sort of error rate. So essentially, we can get rid of the fidelity problem. We can trade off the fidelity problem. We can trade off this error rate problem with more systems, with more qubits. Okay, that's sort of the idea behind error correction, but that's also difficult, right? That makes scaling up the fundamental problem. So what can we actually do near term? And this is something called the NISQ era, the noisy intermediate state quantum era. And I think this is sort of the pathway, at least in the near term, to go forward. We need to come up with algorithms that are more resilient, okay, and that don't require such strict error rates. And the fundamental concept behind most of these NISQ era algorithms is to use quantum systems for what they're good at, which is representing quantum states. Okay? We don't need to represent and do classical things in a quantum way necessarily, right? We should use the quantum systems to do something that's fundamentally quantum. And this goes back to what Richard Feynman said, that you really want to use, if you want to have a quantum mechanics inside of your problem, you should make the quantum parts of the problem quantum. So here's just a very generic flow chart of how many of these so-called iterative algorithms work, is you have some quantum state, which is represented on quantum hardware. This is the only quantum hardware you need. You do some measurement, you get that information, and you do all the data analysis and the decision making on classical hardware, right? Classical hardware is great at deciding what to do, it's great at analyzing data, okay? And then we feed back onto the quantum hardware to do something different, okay? So the general idea is basically we want to try to offload tasks to classical computers whenever possible. We don't want to do, the whole point is you don't want to do everything quantum. This is the sort of the NISQ era sort of approach. You leave the quantum mechanics for things that actually represent, that actually require quantumness. And in these algorithms, that tends to be representing states of atoms and things like this. Things that we talked about where you would need like 10 to the 30 sort of components. You let nature handle those 10 to the 30 pieces of information. Nature will hold it. Nature will somehow calculate with it. It's miraculous, but that's an interpretation problem. And it will figure out what will happen. But then you do what you can do classically, just classically. Don't offload that to quantum computers. So I do want to say something about whether you expect these to come to a Best Buy near you anytime soon. And is there any hope for quantum computers in your home? What I will say, my personal opinion, is probably not. The reason why is because they're quite big and complicated, at least in this example. And by the way, this is only like 50 qubits, so imagine what, I know, thousands would look like. But I think the way that, and this is sort of, the way you can use, the way that you can use quantum computers right now is you can use them on the cloud. Basically, companies like IBM have put these quantum machines on the cloud with internet connectivity, and you can talk to them and run quantum algorithms on it. If you're interested in this, you should really look into IBM. IBM, you can do this for free, I think through a package called Qiskit. I think you can also do it for money. It might give you some priority. They are selling these things. Quantum mechanics companies are, I don't think they're quite profitable yet, but at least they are now making money by trying to sell usage of these quantum computers, the ones that I was just talking about, and using them on the cloud, meaning using them via the internet. But I don't want to be so pessimistic that you'll never see them in your home, because this is what a classical computer used to look like. This is a scale. I mean, I think a person standing here would probably take up this entire frame, and this is what classical computers used to be. So hey, you might never know. Now you have a computer in your pocket, probably, in your smartphone. So I don't know what will happen in the future, but at least the quantum computers as they stand right now are quite unwieldy and mostly accessible through the cloud, I think, is sort of the near-term future. Okay, so for that, I'd like to wrap up the talk with a few takeaways. I hope that if you want to take anything away from this talk, these are the messages I want you to have. Basically, quantum mechanics, which was ultimately discovered via experiments, right? It's an experimental science, that's why I focused on the experiments. Not so much the interpretations. I didn't quite say why these things, why particles behave like waves, but through experiments, we saw that particles behave like waves and waves behave like particles, right? We saw single electrons, which are particles, diffract, constructively and destructively interfere with each other. And because these particles are waves, they can be in multiple places at one time. They can be in multiple states at one time, the so-called superposition. And that superposition can be leveraged for computation. You can check a lot of things all at one time. Remember that Grover's algorithm where you had many, many boxes. You can check them all at the same time. But these qubits, these superpositions are very fragile, right? You need to maintain this harmony between all these different probabilities and make sure that they're not disrupted. So they're very fragile, which makes sort of fidelities of current systems very low, and we only have about 100 qubits, which is far from what is required, I would say, for everyday applications. But maybe I'll say one more thing here that Google has claimed something called quantum supremacy, and it is true that quantum computers can do things that classical computers cannot do already. This is true. But I would say what Google showed was hardly a useful thing. So we're far from sort of useful quantum computation. It's kind of like a technical result. Okay, and with that, I hope you learned something about quantum computing today, and I'll take any last minute questions.
Great, thank you so much for your talk. As a final reminder for those of you joining us on YouTube, type your questions into the chat and we'll relay them to the speaker at any point. Yeah. So, do you have any questions?
So, how much money does it cost to build one of these computers? You're saying like startups are doing it, and if I were to want to make a startup, which I'm not, I'm a biologist, this is all very far out of my field. How much money would I have to raise? Do I need to get Bezos to fund me, or is a couple $1 million enough?
Yeah, so the question is how much money do you actually need to create a quantum computer? I believe we're talking about commercializing these things, we're talking about like hundreds of million. I think that's how much IonQ has raised. IonQ has also gone public, so you can buy stocks of them, and obviously Google and IBM have a bunch of money. So I think we're really talking about the hundreds of million right now for the R&D. I think once they figure everything out, an individual quantum computer I think is unlikely to be that expensive. Obviously, it depends on the number of qubits. To run a lab, to give a sense, I think our lab spent like $500,000 in the last year or something like that. So we're to build a quantum computer in a lab, we're still talking hundreds of thousands to $1 million or something, millions.
So very interesting talk, thank you. We're going back to our passwords being in danger.
Yeah.
What if is that all in the sense of like classical passwords? So what if like quantum computers became actually available? Is there also efforts making the passwords also like encrypted?
Yep.
In a better way?
Yeah, so the question is basically, let's say we actually get Shor's algorithm to work and our passwords are in danger. Is there any solution to that problem? I will say, I'll just make one remark first, is that I think this is why governments are very interested in this, because in some sense this is a technology which is, kind of whoever gets it first can wield, very large power. But I would say, yeah, but there are ways around this, and that is to sort of make your communication fundamentally quantum. So there is a whole field of quantum communication and quantum cryptography where you can basically make your communication quantum. It's not necessarily a quantum password, I don't think I would describe it like that, but you are making your communication itself quantum. And just a brief note about how that tends to work. How that tends to work is that because your communication lines are quantum, maybe through like a fiber or something, optical fiber or something like that, you're sending things that are in fragile superpositions. You're sending things that are very vulnerable to the environment. And these methods tend to work by using this idea of measurement, that if somebody wanted to read your information, they will change the state of your system, they will measure it. So it's more about knowing that there's an eavesdropper rather than preventing eavesdropping from happening. That's my understanding as far as how some basic quantum cryptography works. Yeah. And I will say that's probably more advanced, more technologically advanced at the moment than like quantum computers. So that's a good thing, that I think the protection is a bit more advanced, I think.
Any other questions? One of the things that I always like to ask of our speakers is, what brought you to this field? Like, what excites you or interests you, or anything you want to say about the work that you do with this?
Yeah, so what got me into this field? In many ways, it's quite serendipitous. For me personally, my freshman year, I was asked, who I wanted to be my advisor, and the person in charge of the physics department said, okay, how about John Doyle, who's a physicist that works on these atoms, molecules, and things like that. And I was like, sure, I don't know who this is. You can just pick whoever you want for me. And through conversations with him and him giving me the opportunity to work in his lab, that's sort of where this came from. But I will say, from a fundamental perspective, I've always been interested in understanding things very fundamentally, very down low levels, where you can really work on individual atoms, individual molecules, where you can actually write down what is happening in equations. I've always liked that part. But what is really cool about this is that it's also very useful. It's not just something that people just think about and then forget about. It's really something useful. So it's this combination of being able to understand something fundamentally and with the practical applications, which I hope to convey in this talk.
If we don't have any other questions or for YouTube, then I'll say great talk once again. Nice job. And then this is the last seminar in the series, so we won't have another one next Wednesday at the same time. But if you want to watch this talk or any of the other talks from this year or years past, they're uploaded on our YouTube channel. So feel free to watch this on your end. Thanks for joining us.
Thank you.